Really good. It's just simple enough. It's a bit tricky, but I'll go through all of that. So FlatCam. The way FlatCam works is you import each layer, and each kind of output file goes through a bunch of sort of processing, and then you get a G-code file for each operation that you're doing. So basically, I'm going to open the drilling file first. The holes are in a Excelon file. It's basically a TXT file, text file, which drill. Here we go. Yeah, it's just text file with all the coordinates in there. So as you can see, it opens up. Now this is kind of like just the vector file. So you select the vector, the input file, and then you move into the operations that you can do with it. Actually, just before we do that, I'm just going to set up the units here. Project options, millimeters. I'm using millimeters. I don't know what. I'm going to switch that over and switch that over. Okay, cool. Yeah, so we're using millimeters here. We haven't created anything yet in FlatCam, so we don't need to redo anything. We just got the input file at the moment, so select that, and then you've got the operations in this next tab here. So whatever's selected, this is context sensitive, so it gives you like the options of what do you want to do with this file. So at the moment, we basically want to generate the code for the drilling. It gives you the totals for the drilling for all the different sizes that have come in the Excelon file. You can obviously in FlatCam and other PCB design software, you can customize your hole size. What I usually do is just use one drill bit for everything. I use a 0.9 mil PCB drill in this CNC machine. Just do everything with that, and then and use that as a pilot hole to enlarge the larger holes, like the holes for the serial connectors and the main connectors, and then the some components really thick don't fit, just enlarge them. So that's easy. So basically I just select all of them using the shift key. Just it's a bit fiddly doing this, but you select the first one, hold the shift, select second, third, scroll down, fourth, fifth, sixth, seventh, and generate. But you just need to make sure these parameters are correct. So the cut Z is the depth of the cut. Now most PCB boards are less than 2 millimeters, so I'm just going to do 2. They're still selected, yeah. So 2 mil, fine. Travel Z is the height at which the drill bit will travel from hole to hole. Now if you've got things that are like fixtures or bolt like screw heads that are sticking out, if you're screwing down your PCB board, you need to make sure the drill bit will clear those, otherwise it will crash and break. I'll just use 2 mil. I don't know how I'm going to hold this down yet. I think I'll probably just cut some holes in the actual board itself. I think this shouldn't really bow too much because it's copper on both sides, so they tend to be quite flat boards. Anyway, feed rate, that feed rate is fine. You can actually adjust the feed rate in Mach3 when you load it in. It gives you up to 300% adjustment, so that's good. This is derived from like an inch per whatever, like a imperial thing. That's why it's such an odd number. But in millimeters, I don't know what it is millimeters per second or something. Or yeah, but this feed rate is adjustable, so not to worry what that says really, as long as it's within the ballpark. So now we click generate. Now FlatCam will look like it's doing nothing. It shows idle, but it is actually working in the background, and some with complicated, sort of a highly populated board like this, where there's lots of holes to do, you just got to be patient and wait. So I'm going to pause the video here. Still going. It's been about a minute. Come on! Get out! It does help if you give it some encouragement. Sometimes. Yay! So it's done it. It's a lot of holes. So, what's the highest number? I think I can see like 516. Yeah, there's about lots of holes there. It's most of the holes are in my little logo thing there. I'm just gonna leave it running. It's set and leave it running sort of thing. So whatever. So now if we go back to project, we can see we've got the CNC file, which is great. So that will give us the option to add or prepend or append. So add stuff to G-code before at the top or after at the end. We've got nothing really to, some people might put like, tool change G-code in here or whatever, but I changed my tools manually because it's just a home built rig. Tool diameter? Oh, why does that matter? I don't know, but it doesn't really matter, I guess. I guess it's just maybe for the plot, for the graphics. But yeah, don't matter. Export G-code. So I'm going to create a new folder in here. Say G-code outputs. MS 2.2 02. Today's date. What's that? 23 03 04 16. There you go. In there. Get in there. Drills. Okay, that's done. Now next layer. We're gonna do the top copper next, I reckon. Now the copper traces are Gerber files. So you need to open up Gerber. Copper top there. Copper top and copper bottom, these ones. Yeah. So the top one here. Load that in. It will hopefully be smart enough to overlay them on top of each other, which it is. That looks great. Cool. Just gonna enlarge this window. Oh god, look at that shugget. Okay. Oh no, too far. Slow, very slow. Oh, one notch of the mouse is perfect. Here we go. Right, so it gives you an outline of the actual traces as they came in from Fritzing. Now what you need to do with those traces is obviously take into account your PCB drill or PCB milling bit, PCB bit size. It's a size. Struggling today. And work out the toolpaths. So we first of all select the input file, which is the copper top GTL. Now with this selected, we want to first generate the geometry. So you need to make sure these settings are correct. Now I can't remember, I don't have like a preset kind of template for this written down. So what I usually do is like I usually use the last project which I did that I know worked really well. So I'm going to open up another FlatCam. You can open multiple instances of this software, which is great. Then I'm going to open a recent file, which is this one. It's just a little board that I did for a friend. It's got the fully done outputs here, is what you can see. So I am going to select the copper top GTL, which is the same Fritzing file, but for a different project. So what did I use? I used tool diameter of 0.45, width passes 1, pass overlap 0.15. Now from trials that I did before, this might not be fine enough to generate a path through the the tightest gaps here, but let's try it. So we go generate geometry, wait for a little bit. This step doesn't usually take that long. Here we go. Yeah, so as you can see, like for example, places where the traces are quite close together here, it's not generated a path there, so that's going to be an issue. So we need to go back to your file sort of browser. So this ISO is what we just generated, so you just need to delete that. Just going to tap the delete key. I don't know which one of these buttons works for that purpose, but the delete key is great. Go back and I'm going to reduce the tool diameter, say 0.3. It's a conical bit that I'm using, so actually the diameter is only it varies with the depth of the cut, so I need to work that out yet. But we still have this problem here, so we still need to make it smaller. Delete 0.25. Getting quite close now. 0.25 should work. Right, here we go, that's better. So that area is fine. I haven't worked out how to pan this view in FlatCam, but I just zoom out. Oh no, there's a way to center it. Center. Zoom in, zoom, fit. Zoom, fit. Yeah, fit, zoom. Nice. Nice, some fit, zoom right there. So I'm looking and I'm trying to spot merged tracks, but I can't see any. It's fine. So what's here? What is going on here? Yep, fine. So the name of the game here is to basically generate the ISO, which is ISO, I guess, is the step before the cutting toolpath, or is it? No, it is the cutting toolpath, but it's not the G code yet. Yeah, so we just need to make sure it's it leaves as much margin around your pads as possible, but it actually goes around every single one. So there aren't any joined up pads, which obviously will cause a short. So it's looking good, right? So I'm happy. Just gonna zoom to fit again. What about my little logo there? that's cool. Yeah, so it's just kind of see where where the holes are tiny. It just approximates them, which is perfect. Perfect. Right, now let's use this ISO file to generate our G code. So just select on the ISO. CNC job is where you set the depths of and the travel height and the speed of your your cutter. So again, I'm going to refer back to my project that worked. So we've got ISO, top ISO, yep. So I'm cutting at 0.1, which is okay. Obviously, I mean, this cutting depth is it's more of a guide, because more of a guide than than a rigid setting, because what happens is if your board is not completely flat, you sort of need to find the highest area of the board, and do a sample cut and see how deep you need to go to, or the shallowest, I guess. Yeah, see how deep you need to go to create a cut, you know, to pierce through the copper layer. So like you need to go deep enough to pierce through the layer, but not too deep that the two sides of the PCB are actually gonna cause full on like holes, you know, in your board. Holes in the tracks won't really affect the electrical performance, but it's just going to make the board, you know, more fragile, because, you know, some of these tracks are going to be kind of, you know, detached from the body of the thing otherwise. So, you know, where they cross over, where the top and bottom layers cross over, well, there's a few points where that happens. Anyway, 1 millimeter in the negative Z is what I go with. Travel Z, I might go for 2 millimeters just to be safe. Feed rate 50 is I don't know if I'm cutting too fast or too slow. I've had issues with quality, but I'm going to go with 50 for now because I can speed that up if that's too slow. Tool diameter. On this board, I set the tool diameter quite high, quite wide, quite large, because I don't have any pads that are really close together. For this one, I'm going to have to go small, and just, you know, suffer the consequences of very, very, very small pads, and just use solder very, very well. So I'm gonna, maybe I'm gonna go with I don't know, 3, just a bit bigger than the ISO. Spindle speed for me is manual, so that's doesn't need to be set by G-code. I set that manually on my variable frequency drive. Cool, so that's done. Generate, and that's when it generates the blue G-code. So one thing to note is that the blue G-code will obviously follow the ISO, which is that thin red line or dark line that it's just generated. It's very thin, I can't really tell what color it is. So the G-code follows that. So when you click generate, no extra toolpath is generated. It basically just follows that ISO. So at this step, whatever we set here won't give us connected pads if our ISO, which is the source for this G-code, which it worked out earlier, if our ISO is is good, then our G-code will be good also. So it's just for, I guess, pre-visualization. So we've generated the G-code file. Now we need to export it. So we select the CNC, which is the G-code, and we export it. So drills, copper top. Now we need to open the copper bottom. Sorry, I'm just having a look at these holes here. Here I've used the preset built-in library components in Fritzing, so it's obviously figured out that it needs to cut around this hole, the mounting hole for the connector. It didn't do the same for my ones because these are just holes that I added, not wires. Generally, the fixing is either plastic or is grounded anyway, so the fact that it's just going to be a hole is fine. We don't really need an island, an isolated circle around it. Anyway, so let's load in the copper bottom. Open Gerber, copper bottom, GBL. You can see from the file size that it's quite a lot less detailed than the copper top. So one thing that happens is the bottom layer is obviously loaded in the same position and the same rotation and orientation as it came out of Fritzing, which is basically the two layers are overlaid over the top of each other. But if you think about this, the CNC machine, it doesn't cut both layers from the bottom and the top. You need to flip the PCB to do the bottom. So you need to do that in the file. You need to reflect that. So how am I going to flip it? Left to right or top to bottom? I want to go top to bottom. So take the GBL. Before we generate anything, we need to. That's when we flip it before we do anything. So select the GBL, and then we have tool. Nope. Tool, double-sided PCB tool. Click that. That gives us the ability to flip it. Now we need to select what we want to flip. So we need to select the bottom layer. You need to select the axis which we're using to flip this. So I'm going to be rotating it sort of up, top, up. I'm doing hand motions, but obviously you can't see me. So top to bottom, basically, as opposed to left to right. And top to bottom means x-axis. The x-axis goes across like that. You know this. You have a CNC machine. Point. I use box, and then I select my box layer. Usually I select the cutout layer, which I haven't loaded in yet, but I'm just going to try and use the same layer here and see if these holes line up. Basically, see if the. Wait, no. How do we make sure that these things all line up? I don't know. You know what? I'm going to load in, before I do this flipping, I'm going to load in our cutout code. That's just how I've always done it. I don't know if this flipping this using that as the guide would work, but I've used it differently in the past. I've done it differently in the past, so I'm going to do it like how I know works. So we open up another gerber, which is the cutout, which is what, contour? Yeah, it's the contour file. And the contour file is basically just the outline border of your board. Border of your board in Fritzing. Here we go. Where the light grey ends and dark grey starts. This is your cutout. So what I do is I'm kind of doing this. I'm kind of going back on myself now. But basically, okay, let's return to the to cutting the copper, and we'll leave the contour to last. So let's flip the copper board, the bottom copper. Select it, tool, select what you want to flip, select the axis, find axis locations, the box, and then we use the contour as the flipping guide. Mirror object. It's actually mirroring, not flipping, so I'm kind of using the term wrong, but you know what I mean. So yeah, we've just mirrored it on the x-axis. This is quite confusing now, but yeah, so we go back now. We have now flipped our source for the bottom copper. Now we process it like we did with the top copper. So what were the settings we had for the top? Copper top GTL, this guy. Diameter 0.25, width 1, pass overlap 0.15. What was that? 0.2. Okay, copper bottom. 0.25. Oh, that would have been a mistake. Cool. Update geometry. So that creates us the ISO. Oh, don't crash now. Phew. Okay, cool. Now in theory, all our tracks should be nicely separated. I'm just going to verify that by switching everything off, or as in how do we disable all plots but this one. That's what I need to do. So select the copper bottom ISO, disable all plots but this one. Just going to clean up our viewer here. Strips them down one by one, and here we go. Right. Oh, that's much better. Oh, danger. Quite close together there. Okay, there's one point. Oh, another point. Oh no. I kind of hoped it would be. Ah, what's that? What's that there? Let's have a look. That's where is that? That's bottom. Do they need to be connected? Can't tell where that is. I don't know. Let's have a look at the copper bottom gerber. Need to generate it. Replot. Come on, come on. Enable all. No. It's gonna take a little while. Are we done? Are we done? Oh, nearly there. So I'm gonna save it. I wanna freaking save it. Save project as. Okay, more done. We're checking the bottom. Checking the button. Disable all plots but this one. So this is a problem area, but I'm going to tidy it up manually because I don't want to shrink the shrink all the tracks just for this bastard here. So I'm going to clean that up manually. So alright, let's carry on. Copper bottom, what have we done? We've made the ISO file. Yeah, that's cool. So that's the internal, like the routing toolpath file. The isolation routing net, I guess you could say, or whatever you call it. No, I'm not an expert. Yeah, use the previous settings that we used for the top. What are they? Cut Z. -1, +2, 50.3. -1, +2, 50.3. Ah, did I increase? Oh no, I didn't. Cool. Generate. Now we wait. All right. Here we go. Oh damn! I just really don't need this. This is gonna take ages. Oh well. So we've got the ISO CNC. Now we need to export it. So let's have a look at the settings. There's no settings. It's great. Oh, hit that by accident. Select. Export G code. Amazing. Copper bottom. Now the only thing left to do is create the cutout, and the way I usually do the cutout is we've got the contour file loaded in. We just enable all the plots again, and then yeah, just keep them all on screen. It's fine. FlatCam is great software, but it is quite slow. But I don't blame the developer because this nice guy who decided to make it and release it. So, Jesus, I mean, it's free. Like, props to the guy. I'm not going to complain. Okay, contour. The contour it's kind of, I mean, I believe FlatCam has the ability to create a cutout of the board just based on the furthest, the distance that's furthest away to the components, the tracks that are furthest out on the edges. It kind of works out a margin, and it can do that automatically. But we actually have a sort of a vector file for the border, and we can basically create a G-code for cutting that in the same way as we create the G-code for cutting the track. So I mean, that just makes sure that the size is decided by our PCB design software, which is Fritzing, as opposed to FlatCam. So select the contour. Board cutout is what we need to do. Tool diameter. What is the tool diameter? It's a cone, so it's gonna be deep. I guess it doesn't really matter as long as it's within the ballpark. And I'm gonna refer back to my known working project. Contour cutout. Oh no, GM1. Contour GM1, yes. Here we go, board cutout. Tool diameter, 1 mil. That's quite large. I'm gonna go smaller this time. 0.8 millimeters. No, do you know what? I'm gonna go 1 again because I'm going to be reducing the angle of this tool. So I need a bit more margin. Margin. That's what I need. A bit more margin. Bit larger tool. And don't mind if we get extra margin around the board. It can be trimmed back, but if we manage to damage some of this track here, then that's not going to be very good. So where are we? Gap size. Okay, so tool diameter, margin are your two main components. Gaps, you need to decide like how many tabs that are uncut you want. 4 tabs makes sure that the board stays rigid for multiple iterations of this same code. So for example, if you have a small PCB and you have if you have a small design and you have a large board and you're making 20 of them in one go, then you probably want to keep more tabs, so more gaps, more gaps, and the gap size, you want to keep that quite high because you don't really want to compromise the stability of your sheet of copper clad board the further you progress through your job. But this means there's a bit more manual work actually popping out these things when they're finished. But what I usually do for a single design, the least amount of work post CNC is to do 2 tabs, top or bottom or left or right. I don't know. Let's do top and bottom because that's the larger side. Gap size. Do you know what? PCBs are quite strong, and I used 2 here. I could probably even go smaller. For this, because I'm only going to cut one of these. Again, it's only really going to get wobbly if it is right at the end, and right at the end I can just put my finger on it and make sure it doesn't pop out or get in the way of the cutter just as it's finishing the cut. That's assuming it gets loose. It's not going to get loose, so I'm just going to say I give it a really small gap, like 1 millimeter gap. So that's going to just mean I can literally just pop it out, snap it out really easily. And here we go, you can see what the gap is there. It's going to be less work later. So now we have the cutout. Again, we need to generate the CNC job. So cutout, what are our settings? cut depth is going to be 2 millimeters. I use 2.5 here. That's too deep. It's actually marked my board, my bed on which it all sat. So travel again 2. Feed rate fine. Tool diameter 0.5. Just round it up. Again, that doesn't really matter. Like whatever. Generate. And that's going to turn blue, giving us a nice wide margin here. So it means with a conical bit, you can go really deep, still have a little bit of a border. Now, if this board has, if you have a case to slide this board into, you have to pay a lot more attention to how you do this, because you can actually, if you're very careful, you can create very precise size, down to like 1/10 of a millimeter. I don't really care. For me, I'm probably going to mount this flat or on standoffs on something, like a piece of, panel of some kind, or I might put it in a case. I might 3D print a case. Who knows? It's crazy. So play it by ear. So we've got the CNC. Let's export it. Cut out. Cool. Done. That should be everything. I've got a trial version of Mach3 on this computer. I'm going to load these files in and just check out see how they come out. Reset, load G-code. Libraries. Google Drive, electronics, Fritzing, Gerb output 2, G-code. It's not a tap file, it's actually a text file basically, but so you have to change your output, change your file type to all. Yeah, let's just see copper top. I mean, I know this is going to work. I'm just doing this for preview purposes to show you guys. So here we go. That's pretty cool. Looks cool. Now, if we want to make many of these, what I usually do is use the nesting wizard. Nesting wizard in there. The nesting wizard requires you to place an M99 instruction at the end of your G-code. So you could put it in you could put it here, M99, or you can open the G-code files manually and do it. There's also another thing which it needs, which no one mentions. Well, if you find that the nesting wizard doesn't work, I don't know if you need to delete this or just tag M99 after. You need to put a semicolon. No, it's not a semicolon. I'm sorry, it's a % sign. And for some reason that makes it work. Sorry, I can't be more descriptive as to why it works, but I think you need to might also need to delete the semi-file. Let's check out the nesting wizard. I'm not going to do this. I'm just kind of doing this for your benefit. If you want to do nesting, this instruction here says end with no M9. I replace M13. We don't have an M13 in our file, so we're good. Just put M99 and then we put a % sign. Let's try it. Eh? This is the file before I did anything to it, so we're going to return to Mach3, close it, close the file, and I'm going to save this out. It doesn't matter if you're not nesting it. If you have this M99, I think it throws up a little error. I think that means like looping, so that means like when you're finished, go back to the start of the code, I think. But again, like if we've just finished it, Mach3 will be like, okay, looped, but where do I go? What do I do now? It'll throw up an error, but it won't actually, ruin your part or anything like that. Alright, so I've just loaded. Yeah, here we go. Return called with no sub in effect looping. I don't know what that means really, but it's fine. Or is it? It's been fine for me so far when I've done this on my other machine where I have Mach3. What are you doing? Why are we waiting? Do I cancel? I'm gonna pause the video and wait. Just see what happens. It's still here. It's not done it. So, what do we do? What do we do now? Let's close it, load it again. See what happens. It's having problems generating this thing, which is weird. Why is this? Why are you doing this to me? M99 percentage sign. Yeah, that's what we need to do. Maybe, well, it actually looks like it's loaded the file. It's just not giving us a preview, a visual preview for it. Which I guess doesn't matter if we're if this nesting wizard has accepted it as a G code. So let's do it. I think this is the dimension of a board. So yeah, let's leave that. So we want 2 boards in that axis, and then two. Oh, you have to press enter. 2, enter. Click 4, enter. 2 in that axis, 4 in that axis. Create file. So yeah, what this does is creates a kind of a parent G-code file. Here we go. Yay! Look at that. It creates a G-code file, which basically is like says, okay, Mach3, open this this G-code file. Go to home, and then go to here, and then like set your home position as a new position, and like proceed, you know, with like doing it. And then it kind of repeats it, but then it moves to a different position and it sets a new home. So like every time your source code completes, it comes back to the parent file. So when you return to Mach3, what it does, it actually loads in this parent file, which includes your original file that's like nested inside it loads of times, so 8 times in our case. And yeah, we just get this humongous job file, which is great. So in theory now it should just go away and do its thing. Let's do it. Let's see what happens. Start file. Here we go. Just doing it. Look at that. Whoa. Where are we? Just going extremely slowly because my units are messed up in this Mach3. I haven't set this up, so I just use it for previewing, just making sure files load and whatnot. Yeah, I think it's in inches or something. I don't know, but it's working, which is great. So let's stop that. Stop, reset, close. Don't want you anymore. Here we go. Yeah, so thanks for watching. I hope that's clarified the workflow for you. It's been a very long video. Apologies. It's an hour long. Oh my god. But yeah, good luck. So the CNC process is complete, and the board looks great. The process of the way I did it is probably not the right way to do it, but one of many ways to do it, is securing the the copper clad board to the bed of my machine with nails or screws or whatever, and then doing the top layer, the holes, and the cutout. Now the holes in the corners here, where I this hole here, and that one there, and that one there. These are made for alignment purposes. So when the board is cut out and flipped, these holes can basically just be used for to make sure that the board is placed in exactly the same place as it was before. So what this means is drilling the bed to slightly smaller diameter than this pin. These pins are called panel pins. They're essentially nails. I got these from Wix, and this measures out at 1.5 millimeters. I drilled the hole all the way through into my bed at 1.4. I think I had a drill bit that measured slightly under, so that's a nice tight fit. And then I enlarged this hole to about 1.7. Just basically means that the pin goes through this board very easily, and with a very, very small amount of play, probably like less than 1/10 of a millimeter. And when it goes into the bed, it's actually a friction, an interference fit, so it's not going to move, and it provides pressure holding the board down. So that's the way I did it. I flipped the board over. Sorry, the board was like this. Cut the board out, flipped it over, put these pins back in, and yeah, it was in the same place. The alignment isn't 100% perfect, but it's good enough. It's not quite. It's good enough that the holes are inside of the pads, and they don't actually break the pad. So that's great. The pros of doing it this way are it's very cheap. I mean, this board to buy this board costs probably about £5. That's all you need really. These pins are also very cheap. This board, fabbed by Fritzing or bought from a supplier, probably would cost in the region of 50 to 100 quid or 100 bucks, depending on where you buy it. This particular board is very, it's quite a well-known thing. It's quite a well-known design. It's not a one-off. So there are places online where have basically made loads of them, stocked them up, and you can buy them cheaper than what it would cost you to get one prototype from a fabrication house, as a one-off. So that's good. But I mean, we're still talking about the ratio of 100 bucks to like 70 quid to 7 quid, if your time is free, of course. So that's the pro. The con is it's tricky to solder components to this board, because if you drill the holes, do the isolation, routing, and the cutout all in one go, the top layer and the bottom layer aren't going to be connected through your holes. So what you have to do is basically solder you have to make sure there's access. Make sure you can access the legs of your component through the top and from the bottom, and solder them from the top and from the bottom. So the leg of the component, just got on a broken resistor here. The leg of the component essentially connects the two halves of the board together, provides a bridge. Now if you can't access the top, like for example if you're soldering a header, a serial header, or where it's blocked from one side and you can't access these pins, I'm going to basically try using solder paste, putting solder paste on the pins and then pushing the component through, and hopefully the solder paste kind of creates a little ball of solder on the top layer, and then when you solder it from the bottom, the heat will hopefully fuse it to the top as well. I haven't tried this yet, but it seems a hell of a lot easier than going through the plating process. So that's another way of doing it, the plating process, and that involves you drilling the holes first, dunking the board into a plating rig, which is a vat of solution and an electrical anode and a cathode, and a constant current being applied to both of them, and the ions basically plate the surfaces of the object in copper, including the holes, so your tops and your bottoms are connected. Then you proceed as usual, doing the isolation, routing on the top and the bottom, and obviously don't drill the holes again, because the holes are already covered in copper. You can also use rivets. I think I've seen online people using tiny little rivets, but that involves making sure your hole is big enough for that rivet to go through, and you have to press these rivets. I think it's probably about 200 holes in here, and that's a lot of labor. So I'm going to try doing it this way, and yeah, hopefully it works out. I might post an update video on how this goes, but it's part of a longer term project, so probably not going to be for a while. So anyway, thanks for watching, and I hope you have success doing this yourself. Cheers.